Good morning, guys.
Good morning, sir.
Okay, so we have 15 students present so far. So should we wait for some more time for others or we can start? All right, then I think we should start. Tell me what we were discussing in the last class.
Sir, we were discussing about the graphs.
The graphs. The graphs are done.
Yes, so we have to start with module 4 today.
All right. We have to talk about normal distribution then. Very good. Okay, so anyone who read about normal distribution, what is this, why we use it, or any information that you guys can give me? All right. So first of all, tell me how many data types we studied in our first class? Yes, who will tell me? Anyone who can tell me the data types that we studied in our first lecture? No one knows it. Yuvraj,
What's up?
types of data. Or types of variables. Don't know it?
No, sir.
So if you remember, I told you guys that the variables are of two types, qualitative and quantitative. Okay. So qualitative data where you check the quality and you basically do the counting there. So if I have to find out, say the gender is a qualitative data. So you check the quality. I mean, either someone is male or female and you count them. You don't measure them on a scale. While the quantitative data is where you measure something. That can be height, that can be weight, that can be blood pressure. All right. And you don't count, you basically measure it. So if you measure something, depending on what kind of scale you are using, you can expect any value. All right. So what this fourth module talk about, it talks about how these variables, either it is qualitative or quantitative, how they are distributed in the population. Okay, so we'll start with the distribution of quantitative data, and that we study through normal distribution. Okay. So for that I need to show you guys two videos basically. Okay, so let me share these videos first, and once we are done, then I will explain it with a certain example. All right. Okay, so let me share it with you guys. All right, so you guys have to watch this video first, and I'll ask some questions, and then I'll show you another video.
In this video, we will be learning about density curves and the properties of density curves. But before we talk about this, we have to do a bit of review. Let's say we have a room of 20 people, and we record each of their weights. Then, we take this information and create a histogram. Recall with any histogram, we can transform a regular frequency distribution into a relative frequency distribution. The only difference between these two is that a regular frequency distribution tells us the number of people within a given interval, whereas a relative frequency distribution tells us the proportion or percentage of data values within that same interval. For example, there are 6 people that weigh between 100 and 110 pounds. But we can also say that 30% of the people in our dataset weigh between 100 and 110 pounds. To convert a frequency distribution into a relative frequency distribution, we first needed to know the total number of individuals we were working with. In this example, we are working with a total of 20 people. Next, we needed to determine the proportion of individuals in each interval. We did that by dividing the number of people in each interval by the total amount of people. This gave us our relative frequency values. Now you know that you have done this entire conversion process correctly if you add up the relative frequencies of each interval and they add up to 1. The total area of any frequency distribution is always equal to 1 or 100%. So what is a density curve anyways, and where does it come from? A density curve is just the curve that helps us visualize the overall shape of a distribution. If we take the histogram we just worked with, and if we draw a curve around its distribution, we have essentially made a density curve. This can be done with any type of histogram, with any shape, and with any form. And like a relative frequency distribution, density curves always have an area that is equal to 1 or 100%. Now you might be wondering, what's the point of a density curve anyways? Why don't we just stick to using histograms? Well, density curves have a few advantages over histograms. First of all, density curves give us an idealized picture of a population or dataset without considering irregularities and outliers. Because of this, it really gives us a great overall picture of the actual distribution and its tendencies. Secondly, the picture of a histogram really depends on how many intervals you have. The more intervals you have, the better you can see the distribution of the data. But with a density curve, you are not limited by the number of intervals there are, and you can actually have an infinite amount of intervals. And third, a smooth curve is generally easier to work with than a histogram, especially when you are working with very large populations. Now the use of density curves becomes more practical the larger your population is. If we made a histogram from data we collected from 50 people and drew a density curve over it, we have a lot of missing gaps. And because of that, our density curve can be inaccurate. Now imagine if we had a population of 100,000 people instead of 50. Because our population is so big, we can continuously reduce the length of each interval we have until we end up with so many intervals that we essentially end up with a histogram that can be accurately represented by a density curve. This is why density curves are so valuable. They aren't limited by these intervals, and they can be very useful when working with very large populations. We can also use density curves to make approximations. For example, if we have a density curve that represented the test scores of 1 million people, by looking at the curve, we can say that half of the people scored over 60 on this test. We can also say that a large majority of students scored between 50 and 70 because there's a lot of area contained within this region. We can also say that only a few students did very well on this test because there's only a small amount of area contained within the upper tail region of the curve. You'll know how to calculate these exact areas in an upcoming video. But now that you know what a density curve is, we have to go over some very important rules for having a valid density curve. In other words, we'll have to talk about the properties of a density curve. The first rule is that a density curve must lie on or above the horizontal axis. Density curves that are drawn along the y-axis or ones that dip below the x-axis are invalid. A density curve has to sit on the x-axis in order to be valid. The second rule is that the total area under the curve is always equal to 1. Now if I said that the total area was equal to 5, 12, 70, or any number other than 1, then I do not have a valid density curve. However, if I said that the total area was equal to 1 or 100%, then I do have a valid density curve. This is a very important fact, and it's one worth remembering. Density curves come in many different shapes and sizes. Some are well known mathematically and others aren't. Each type of density curve has its own name. A common density curve you might encounter is the uniform distribution. It is called this because each interval has the same frequency of data values and is uniform throughout the entire dataset. We also have the triangular distribution, and it's called this because, well, it looks like a triangle. And most importantly, we have the normal distribution, also known as the bell curve. In statistics, this is the most important density curve that you should familiarize yourself with. We'll be talking a lot about this curve in the upcoming videos, but for now, it's very important that you understand the concept of density curves. So let's do some practice questions. Feel free to pause the video at any point so you can try these questions for yourself. Question number 1. For the density curve below, approximately what percentage of people weigh exactly 150 pounds? A common mistake that students make in these types of questions is they see 150 on the graph. They draw a line and then they see that it lines up with 0.20, so they will say that the answer is 20%. Now this is incorrect. Remember that the total area of a density curve is always equal to 100%. This line definitely does not have an area of 20%. In fact, the area of this line is equal to 0 because a line has no width. As a result, the answer is equal to 0. Logically, this makes sense because realistically, no one will ever weigh exactly 150.000 pounds. Usually, you'll have some measurements very close to it, like 150.5, 150.70, 150.05, and so on and so forth. However, if I asked you what percentage of people weigh between 150 and 152 pounds, then we have this entire area to account for. We can actually get a rough estimate of this area. We know that the area of a rectangle is equal to the length times the width. We have a length of 0.15 and a width of 2. Multiplying these together gives us an answer of 0.30. However, we still have this top portion to account for. To estimate this area, we see that it is almost equal to half of a square. The area of a square is equal to its length times its width, which is equal to 0.05 times 2, which gives us 0.1. And half of 0.1 is equal to 0.05. Therefore, the total area is roughly equal to 0.05 plus 0.30, which is equal to 0.35. As a result, the percentage of people that weigh between 150 and 152 pounds is roughly equal to 35%. As I mentioned before, you'll know how to calculate these exact areas in an upcoming video using a different method. Question number 2. For the uniform distribution below, what must be its width in order for it to be a valid density curve? We know that the area of a rectangle is equal to the length times the width. Algebraically solving for the width tells us that it is equal to the area divided by the length. We know that the area of any valid density curve is equal to 1, so the area is equal to 1. We have a length of 8, so 1 divided by 8 gives us an answer of 0.125. Question number 3. For the uniform distribution below, what proportion of values are located between 12.3 and 18.6? On the graph, 12.3 and 18.6 is located somewhere around here. This is our area of interest. Now we know that the area of a rectangle is equal to its length times its width. The length is equal to 18.6 minus 12.3, which gives us an answer of 6.3. And the width is equal to 0.05. Multiplying these together gives us an answer of 0.315. This means that the proportional values contained within this interval is equal to 0.315 or 31.5%. If you found this video helpful, consider supporting us on Patreon to help us make more videos. You can also visit our website at simplelearningpro.com to get access to many study guides and practice questions.
All right, guys. So I hope you got something from this video. So any doubts, any questions, anyone? No doubts, no questions. Okay, so this video basically tells you if you have to plot your data, and if you're dealing with this quantitative variables, so instead of histogram, plotting this density curve is always better. Why? Because then you can calculate the area under the curve. Okay, and why do you need to do this? So that I'm going to explain in that is being explained in the next video. Okay, so let me show you the next video. Then I will talk about it.
A big part of my role. And Grammarly helps me feel confident.
In this video, we'll be learning about the normal distribution and the 689599.7 rule. When we talk about normal distributions, we refer to data we get from a population or sample. So before we actually talk about the normal distribution, we need to first distinguish the difference between a parameter and a statistic. A parameter is a number that describes the data from a population, whereas a statistic is a number that describes the data from a sample. Examples of parameters and statistics are the mean and standard deviation. But because of the definitions we just talked about, we have to be very careful with what symbols we use to represent these numbers. When we are dealing with a sample, we use the symbol x bar to represent the sample mean, and we use the letter s to represent the sample standard deviation. These are statistics. When we are dealing with a population, we use the Greek letter mu to represent the population mean, and we use the Greek letter sigma to represent the population standard deviation. These are parameters. The population parameters mu and sigma are very important when we talk about normally distributed populations. So what is a normal distribution anyways? A normal distribution is a special type of density curve that is bell-shaped. For this reason, the normal distribution is sometimes called the bell curve or the normal curve. The normal distribution describes the tendency for data to cluster around a central value. In fact, this central value is the population mean mu, which is always located in the middle of the curve. So for any normal distribution, we can say that some data points will fall below the mean, other data points will fall above the mean, but most of the data values are located near the mean. The normal distribution and its shape actually arises from many different variables found in nature, such as weight, height, volume, blood pressure, and many more. This is why the normal distribution is commonly studied. For example, exam scores are known to follow a normal distribution. Some people do great on exams, some people do poorly on exams, but a large majority of people score near the average or the mean. In this example, the average exam score is 50 because it is located in the middle of the curve. Now that you know what a normal distribution looks like, we need to talk about the population mean mu and the population standard deviation sigma. Both of these tell us important information about how the normal distribution looks. We'll talk about the population mean mu first. The population mean mu characterizes the position of the normal distribution. If you increase the mean, the curve will follow and move towards the right. And if you decrease the mean, the curve will still follow and move towards the left. This happens because the data will always cluster around the mean in normally distributed populations. As a result, the value of the mean determines the position of the normal distribution. On the other hand, the population standard deviation sigma characterizes the spread of the normal distribution. The larger the standard deviation, the more spread out the distribution will be. And the smaller the standard deviation, the less spread out it will be. Notice that when the spread increases, the curve gets much flatter, and when the spread decreases, the curve gets taller. The reason for this is because the normal distribution is a density curve, and the total area of any density curve must remain equal to 1 or 100%. So changes in the width of the curve must be compensated for by changes in the height of the curve, and vice versa. Overall, here are some points about the normal distribution. The normal distribution is unimodal. This means that the distribution has a single peak. The normal curve is symmetric about its mean, so you can clearly see that the distribution can be cut into two equal halves. The parameters mu and sigma completely characterize the normal distribution. The population mean mu determines the location of the distribution and where the data tends to cluster around. The population standard deviation sigma determines how spread out the distribution will be. The notation given to a population that follows a normal distribution can be written like this. Although it looks scary, it means what it says. For the variable x, it follows a normal distribution and has the mean mu with a standard deviation of sigma. Now that you've been introduced to the normal distribution, we can talk about the 68, 95, 99.7 rule. If we were measuring the heights of all students at a local university and found that it was normally distributed with a mean height of 5.5 feet and a standard deviation of half a foot or 0.5, we can construct a normal distribution as follows. From here, we can create intervals that increase by the standard deviation. So we'll have 6, 6.5, and 7, and on the other side we'll have 5, 4.5, and 4. So what the 68, 95, 99.7 rule says is that within one standard deviation away from the mean, it contains a total area of 0.68 or 68%. Because of this, we can say that 68% of the population are between 5 and 6 feet tall. And if you go 2 standard deviations away from the mean, it contains an area of 95%. This means that 95% of the people in the population have a height between 4.5 and 6.5 feet. And finally, within 3 standard deviations away from the mean, it contains a total area of 99.7%. This means that, for the population we are studying, 99.7% of the people are between 4 and 7 feet tall. Now you might be wondering, what happens if we go 4 standard deviations away from the mean, or 5 or 6 standard deviations away from the mean? And to answer that, you actually can. A normal distribution actually never touches the x-axis. It continues on to infinity. So you can go as many standard deviations away from the mean as you want, but the area contained within these regions will be very, very small. The 68, 95, 99.7 rule is a great way for approximating the areas of a normal distribution, and this works for any normal distribution no matter what shape and size. So let's do some practice questions. Feel free to pause the video at any point so you can try these questions for yourself. Question number 1. The normal distribution below has a standard deviation of 10. Approximately what area is contained between 70 and 90? In this question, we know that the population mean is equal to 70 because it's in the center of the distribution. We also know from the question that one standard deviation is equal to 10, and we can see this because each interval goes up by 10. According to the 68, 95, 99.7 rule, we know that there is an area of 95% contained within 2 standard deviations of the mean. 2 standard deviations to the right gets us to 90, and 2 standard deviations to the left gets us to 50. According to the 68, 95, 99.7 rule, this means that there's an area of 95% contained within this interval. However, we are only interested in the area from 70 to 90. So dividing this area by 2 gives us our area of interest. 95% divided by 2 gives us an area of 47.5%, and that is our answer. Question number 2. For the normal distribution below, approximately what area is contained between -2 and 1? In this example, we know that we have a mu of 0 because 0 is in the center of the distribution, and we know that we have a sigma of 1 because each interval goes up by 1. To approximate the area between -2 and 1, we will use the 68, 95, 99.7 rule. We can strategically divide this area into 2 parts so that we can easily incorporate this rule. We'll start with the right half, which goes from 0 to 1. We know that one standard deviation away from the mean gives us 68%, and half of this is 34%, giving us our area from 0 to 1. The next half goes from 0 to -2, but we know that within 2 standard deviations from the mean, we have an area of 95%. Dividing this by 2 gives us the area from 0 to -2, which is equal to 47.5%. And finally, to get the total area contained between -2 and 1, all we have to do is add these two areas together. And when we do, we get a total area of 81.5%. If you found this video helpful, consider supporting us on Patreon to help us make more videos. You can also visit our website at simplelearningpro.com to get access to many study guides and practice questions. Thanks for watching.
All right, guys. So I hope you found. Okay, so now I should explain this normal distribution with one example. So what these two videos have talked about. Okay, so what I was talking about is quantitative variables. So suppose you have collected some data on a quantitative variable, and let us assume you have collected data on heights. Okay, so you collected data from 10,000 individuals. You measured their mean height, and suppose it is 170, and you measured their standard deviation. Okay, and the standard deviation is say 5 centimeters. Okay, so now this normal distribution, what it is telling you, how this data of 10,000 individuals is distributed in the population. So if we consider x-axis as our height, so we have this scale of height. Okay, so this is 170 here, 175, 180, and 185. Similarly, this side it is 165, 160, and 155. All right, and on y-axis you can have anything. You can have number, you can have proportion or percentage. Okay, so either you can plot the number of individuals, you can plot the proportion, or you can plot the percentage. Now what this normal distribution tells you about how this data is distributed in the population. So it tells you a few things. So what are those things? So number one, if you see the distribution, it always shows a bell-shaped curve, right? So this is a bell curve, or it is also called as Gaussian curve, named after the guy who invented this, Gaussian. Okay, so the very first property is it is bell-shaped in distribution. The second property is you have only one peak. That means it is unimodal. The third property is all the three measures of central tendency, be it mean, median, or mode, they are same. So in this case, you calculate mean or median or mode for all the 10,000 individuals, that will be 170 centimeters only. The next property it would show is the shape of the curve is symmetric around mean. That means whatever shape you see on the left hand side of the mean is the mirror image of the shape on the right hand side of the mean. The next property would be as you move away from the mean, so you go this side or you go this side. As you go away from the mean, tail of this curve gets closer to x-axis. Okay. Then the next property is plus minus 1 standard deviation around mean. So average is 170, standard deviation is 5. So plus 1 standard deviation with mean is 175 and minus 1 standard deviation from mean is 165. So plus minus 1 standard deviation around mean, that means, sorry, that means this much area. So this covers 68% of the observations. So the area under the curve between plus minus 1 standard deviation around mean is 0.68. So 0.68. So what is the significance of this? So you can say that out of these 10,000 individuals, if I select a person randomly, his or her height is between 165 and 175 is 68%. ठीक है. So क्या चांस होगा कि अगर मैं किसी को randomly पिक करता हूं, उसका हाइट ये दो नंबर्स के बीच में आएगा, that is 68%. Then plus minus 2 standard deviation around mean. So the area under the curve is approximately 95%. Or in other words, if I select a person randomly, his or her height is between 160 and 180, uska chance is 95%. Plus minus 3 standard deviation around mean covers approximately 99% of the area under the curve. So plus minus 1 standard deviation covers 68%. Plus minus 2 standard deviation around mean covers 95%. And plus minus 3 standard deviation around mean covers approximately 99%. Okay. All right. So tell me, how many people are going to have height less than 155 and more than 185?
So 99%. What was the question again?
Yes, guys. Who will answer me? How many people are going to have height less than 155 or more than 185?
So 1%.
1%. So I'm asking about the number. So if it is 1%, that means it is 100 individuals, right? Since we are talking about 10,000 individuals here, so 1% of 10,000 would be 100. So 100 people will be there whose height will be less than 155 or more than 185. And if I ask you how many people are going to have height more than 185, then what should be the answer? 185 के ज्यादा कितने लोगों का हाइट होगा? So basically this area under the curve वो कितना होना चाहिए?
So 0.5%.
0.5. So almost 50 people will be having height greater than 185. Clear, everyone?
Yes, sir.
All right. Now there is another concept which is linked with. Okay, chalo, let me ask you one question. So what do you think? How many people should have height between 175 and 180 centimeters? ये मुझे कैलकुलेट करके बताओ। वन 175 एंड 180 सेंटीमीटर के बीच में कितने लोगों की हाइट होगी?
So 23.75.
23.75। ओके, सो आपने कैसे कैलकुलेट किया बताओ जरा।
So first like 160 से 180 के बीच 95 है, तो half of it would be
तो 170 से 180 के बीच में होना चाहिए 47.5, राइट? ओके, एंड 170 टू 175 कितना है? 34, राइट? तो 165 टू 175 68 था, तो 170 टू 175 34 हो गया। So you have to subtract this number. So basically 13.5%, or in other words 1350 individuals are going to have height between 175 and 180 centimeters. All right, guys. Now
really if we half like divided by 4, won't the answer would be correct?
नहीं, कैसे होगा भाई?
Oh, sir, it's between 175 and 180, right?
हाँ, ये
तो
देखो ना, ये दिस एरिया, ये जो मैंने अब ग्रीन से आपको मार्क किया है, दिस एरिया, और let me mark with some other color here, ये वाला एरिया, do you think they are same?
oh, all right, sir. Okay, sir.
So you cannot just divide them. So that was what was explained in the density curve. ठीक है ना, इतना एरिया तो सेम है, ये this much, right? अब इसमें तो इतना एरिया बचा है बाकी, और इसका एरिया इतना है, ठीक है? So definitely you cannot divide them into two equal parts, right? So if I ask you questions where the numbers are lying exactly on the standard deviations, so you can give me the answer. Now if I ask you guys something like 172 and 189, ये हाइट के लोग कितने होंगे? So how many people are going to have height between 172 and 189? Then the answer is not straightforward. Okay, you cannot answer that from here. Then you have to go to something called as z-score. So z-score आपको explain किया था in that video. z-score, so z-score क्या बताएगा आपको? It will tell you the area under the curve. So how do you calculate the z-score? So z-score can be calculated by using the formula x minus x bar divided by standard deviation. Okay, so if you use this formula, you can calculate the z-score. Okay, so let us calculate the z-score for 172. So if x is 172, what should be the z-score? So calculate it till second decimal point and tell me the answer. So 172 minus 170 is 2 centimeters, right? And 2 by 5 is how much? 0.4. So plus 0.40, right? So for 172, the z-score would come as 0.40. For 189, so 170 minus 189, sorry, 189 minus 170 is how much? 19. And 19 by 5 would be how much? 3 point how much? 80, right? So yes, 3.80. Clear? So what you have to do, you have to calculate the z-score. So I'm giving you these numbers 172 and 189. So the first step you should do is calculate the z-score. For 172, the z-score is 0.4. For 189, the z-score is 3.80. Now what you guys have to do, you have to go to the standard normal distribution table. So that table basically tells you for a particular z-score, what is the area under the curve. So I'm showing you the table. So that's the table. All right. So how to read this table? So you see on the left hand side, you have z-scores written in bold, minus 3.9, minus 3.8. Okay. And this is only till first decimal point. The second decimal point is on the top, 0.00, 0.01, 0.02. So if suppose my z-score is minus 3.98. So on the left, I have to see minus 3.9, and on the top, I have to see 0.08. So the answer would be 0.00003. So what is the meaning of the 0.00003? If for any value, the z-score is minus 3.98, so the area under the curve on the left hand side of the z-score is 0.00003. So if I want to know area under the curve on the left hand side of mean, so मैंने बोला the total area of the total area under the curve is 1. Mean divides my distribution into 2 equal halves. तो mean का left hand side में भी 50% area होना चाहिए, right hand side में भी 50% होना चाहिए. So in our example where the mean height is 170, तो अगर किसी का height 170 है, तो z score कितना आएगा? 170 minus 170 is 0. So the z score would be 0. तो देखो 0 पे what is the area under the curve? It is 0.50 or 50%. That means if someone is lying exactly on the mean, उसका left hand side में कितना area under the curve आएगा? 50%. Now the calculations we have done, we have calculated two z score, 0.40 and 3.80. So tell me 0.40 के लिए what is the area under the curve? Anyone? जीरो पॉइंट फोर जीरो के लिए एरिया अंडर द कर्व कितना है?
0.65542.
0.65542. Very good. Or if you want to convert it into percentage, then it is 65.5%. Right? The next value that I got was 3.80. तो 0.4 के लिए है 65.5. 3.80 के लिए है 99.99 or almost 100, I would say. Right? So if you subtract 65.5 from 100, तो दोनों के बीच में कितना एरिया बचेगा? 33.5, right? So let me show you this on the graph. So if this is the question I was asking, so 172 will lie somewhere here, for example. यहाँ पे कहीं पे आपका 172 सेंटीमीटर आएगा, राइट? तो इसके लिए when we calculated area under the curve, तो ये जो बताया था area under the curve, that is 65.5, right? तो इस तरफ जो भी area under the curve है, and for 3.8 तो वो आ रहा है almost 100%. वो almost पूरा distribution को cover करता है. वो suppose it is falling somewhere here. Okay, so इसके इधर में this is almost 100%. So if I subtract this area from the total area, so ये जो दोनों के बीच का एरिया है वो मुझे पता लग जाएगा, right? So 100 minus 65.5. So that is 34.5. तो 172 and 189 के बीच में कितना एरिया होगा 34.5%, or in other words 3,450 individuals are going to have a height between 172 and 189 centimeters. Clear, everyone? Any doubts, any questions? All right. If no doubts, then that is all we were supposed to learn about normal distribution. Okay. I would suggest read more on it and try to solve some numericals. And if you face any difficulty, bring it in the next class. All right, guys. So in the next class, we are going to talk about binomial distribution. Okay. So the next topic would be binomial distribution.
Okay, sir.
All right, then. That's all for today. Thank you very much, guys. Bye bye. Have a nice day.
Thank you, sir.